the question asks okay, this question asks us to prove whether the given space along with the given norm form a Banach space or not. So in order to be a Banach space, it should satisfy three conditions. First of all, the space should be a vector space and the given norm should be well defined. Most importantly, the space should be complete with respect to the given norm. Okay, so here first of all we have to have a very good idea about how the space looks like. So the question given that this is the subspace of the sequence space with respect to the two norm. Okay, so in this set each element is a sequence, a complex valued sequence, and each term belongs to complex numbers. Each Zn belongs to complex numbers. The defining condition is for this set is each Zn has finitely many non-zero terms. Okay, so which means if you pick a sequence or rather an element of the given space, that sequence should have only finitely many non-zero terms. So it can have infinitely many zeros there, but sequence should always have infinitely many non-zero terms. Okay. So here we are going to attack the completeness of this space. So in order to prove this is not a Banach space, we are our claim is this is not complete with respect to the given norm. So what does it mean by to be complete with respect to the given norm? So completeness, actually, if we if we construct a Cauchy sequence from the given space, which means if we pick elements from this set and construct a Cauchy sequence, it should converge to an element in the same space, which means if you look at how the Cauchy sequence looks like in this space, each element is also a sequence like this one here. So this is the sequence, this is the so our claim is this space is not complete with respect to the second two norm. So our claim is this space is not complete with respect to the given norm, which is the two norm. Okay, so we must show that the Cauchy sequence of this space converges to a sequence which is not in this space. So if we can find the Cauchy sequence of the space which is not converges to the element in the given set, then our job is done. Okay, so here I took the sequence of the given space as this. So here each element is also a sequence with infinitely many non-zero terms. Here this is only one, here others are 0. So this has finitely many non-zero terms, which is 1, and then it was also 1. So here 1 and 1 half. Here this sequence is also has finitely many non-zero terms, which is 1 and 1 half. So here I define the nth term as this one. So here always depends on the n, we always have a finitely many non-zero terms, a sequence with finitely many non-zero terms, which guarantees this each sequence in our given set. Okay, so this is a sequence of this space, so that is guaranteed because every element we are picking are in the given set. So that is clear. So we have to prove that now our sequence is Cauchy. So we are going to use the epsilon definition here. So here I pick arbitrary epsilon value. So without loss of generality, I pick m to be greater than n. So here now I consider the given norm, the difference between nth term and mth term with respect to the two norm. Okay, so here nth term of the sequence is this term. This term means this sequence actually. So Zn is a sequence of sequences now. So nth term also should be a sequence. So this is what I wrote here. So since I take m to be greater than n, minus m term should be somewhat like this. Here n, here m. So we are taking the difference. By taking the difference, all the terms are cancelled out except n plus 1 to the nth term. It is clear that no. So here here 1 and 1 cancel out, half and half cancels out. Likewise, all the terms should be cancelled out until nth term. Okay. So what left is only n plus 1 term to n term. Okay. Here I use the definition of the p norm. So everybody knows that p norm is defined like this. This is the definition of the p norm. So instead of p I use 2 here because the question given that the use norm is 2 norm. Okay. So here I wrote the same thing as the compact notation. So here this is indices. So here the superscript represent the place in the sequence, and this represent the element. So according to the norm definition, we are supposed to take each term an absolute value, then square it, then took the summation of all the terms, then take the square root of it. So here this is our sequence. We take the first term and square it. 0 squared is also a 0. So we don't want to write all the zeros here. Just take this term, square, take the absolute value, minus cancels out, square it. This term, absolute value, square it. Likewise, until m, you should take the absolute value square, then take the square root of it. Okay. So here finally we are left with this. Okay. So again we can write this as a compact notation as using k. Here n plus k goes to n plus 1 to the m. So easily by subscripting n plus 1 you get the first term, n plus 2 you get the second term, the last term will be 1 over n square. So this is clear. So here, in order to prove this is less than epsilon, we should have an upper bound. So here to here there are several ways to approach this problem. So I took this integral as the as an upper bound because this represents the area under the curve of 1 over x squared. So but this is the discrete sum. So and it is also goes n plus 1 to the m. So finitely many terms now. So indeed this is greater than this one. So by evaluating the integral, you will get 1 over n. So this is easily just evaluating the integral. So we are left with this one because I took the square of both sides. So here I took the square of both sides, so no problem there. So again next I take the square root. Okay, so now we can bring epsilon to the picture. So from this step to this step should satisfy this condition whenever 1 over root n should be less than epsilon. So by subjecting n we get this term 1 over epsilon squared. So easily by the Archimedean property we can choose capital N or rather natural number depend on epsilon which is greater than 1 over epsilon square. So then easily we can use this condition to connect with this one. So finally we are left with respect to this norm, this is less than epsilon whenever m and n greater than this number, so which is 1 over epsilon square. Okay, so here we took first we took arbitrary epsilon value, then we prove that this difference with respect to two norm is less than epsilon whenever this satisfies. So which guarantees this is a Cauchy sequences with respect to two norm in the given space. So now we are done with the proving our sequence is Cauchy. Okay, next thing we are left to do with finding the limit of this sequence. So here this sequence consists with sequences. Okay, so the limit also should be a sequence. So here the nth term now, so imagine n goes to infinity. So when n goes to infinity, here 1, 1/2, 1/3, 1/4, 1/5, likewise you will have infinitely many non-zero terms. Okay, so if the limit sequence has infinitely many non-zero terms, can that sequence be in this set? No, right? So because in order to be in this set, each sequence has finitely many non-zero terms, but the limit sequence of this one is surely consist with infinitely many non-zero terms because natural numbers are infinite. So we can easily say that limit of this sequence consists infinitely many non-zero terms, hence not in the given space, okay, which is the subspace of the sequence space with respect to two norm, which consists finitely many non-zero terms. Okay. So that implies the given space is not complete with respect to the two norm, hence the space, this space, which is the kind of a subspace of a sequence space with respect to the two norm, is not Banach space because this is not complete. So here we attack the condition of completeness in order to prove the given space is not the Banach space.